Hi guys, welcome back to my channel. So what we're going to be looking at in this video is a little bit more complex than the last operations that we have looked at. So we're going to be looking at dividing complex numbers. So here's an example, and I'm using the same two complex numbers as what we had in the last video. Find the quotient of 4 plus 2i and 8 plus i. So to do this division successfully, we need to make sure that the denominator is an actual number, so a real value, not an imaginary number, not a complex number. This is called realizing the denominator. So how do we realize the denominator of something? Well, we're going to use its conjugate to do that. So just as a refresh, the conjugate of a complex number is just the number, except instead of having a plus, we have a minus, or instead of having a minus, we have a plus. So for example, if I had z was equal to 2 plus 3i, then its conjugate is going to be equal to 2 minus 3i. So why is this going to work? Why does multiplying by the conjugate actually end up realizing the denominator? I'll show you. So if I had 2 plus 3i, and some of you who are pretty confident with your difference of two squares rule may already see where I'm going with this. Multiplied by 2 minus 3i is going to be equal to 2 times 2, which is 4, 2 times negative 3i, plus 2 times positive 3i, and then minus 9i squared. So these two terms, negative 6i plus 6i, are going to add to 0. This value here, remember, is equal to negative 1. So when we times negative 9 by negative 1, we'll get positive 9. So we'll have 4 plus 9. And we'll get our answer of 13. So this is called the sum of two squares rule. Since now we're dealing with complex numbers and we have this I squared here, that's going to change this last value. Instead of being the difference of two squares, it's going to make this the sum of two squares rule. So this is a really neat little trick. So if I have the conjugates of two complex numbers and I multiply them together, I'm going to get the sum of the two squares. So let's go ahead and let's apply this back to our original problem. So we're going to make this denominator real, and we're going to do that by multiplying by the conjugate. Now, since I'm multiplying the denominator, I should also multiply the numerator. So using my sum of two squares rule now, we're going to have the sum of 8 squared, which is 64, plus the sum of 1 squared, which is going to be 1. Then we're going to use the distributive law here. So 4 times by 8 is 32. 4 times negative I is minus 4i. 2i times 8 is positive 16i. And then 2i times negative I is going to make negative 2i squared. So let's go ahead and simplify this. 32, and then this is going to become plus 2 because of negative 1 times negative 2 makes positive 2. So 32 plus 2 is 34. Negative 4i plus 16i is going to make plus 12i, and that's all going to be over 65. So when we write this in complex number form, we're going to write this as 34 over 65 plus 12 over 65i. Let's do a few more examples. If z is equal to 3 plus 4i, find the inverse of z. So remember, when we have something that's to the power of negative 1, that's the same as saying 1 over 3 plus 4i. So we can't leave this in this form. We need to realize the denominator. So we're going to do that by multiplying by our conjugate. And in this case, this is going to become 3 minus 4i. Now, using our sum of two squares rule, this is going to become 3 minus 4i over 3 squared plus 4 squared. So this is going to become 3 minus 4i over 25. Now, when we're dealing with these complex numbers, I'm actually going to split up the real part and the imaginary part so that we have 3 over 25 minus 4 over 25i. Let's go ahead and do another example. If z is equal to 2 minus i and w is equal to 1 over 3 plus i, find the real component of z plus w and then the imaginary component of 3z plus 2w. So let's go ahead and start off with problem A here. So we're going to need to find what z plus w is first in order to find the real component. So we know that's going to be equal to 2 minus I plus 1 over 3 plus I. Now, we can't add these two as they are, so what we're going to need to do is we're going to need to realize this denominator so that we can add these two values. Okay, so let's work on that first. So 1 over 3 plus I. We're going to multiply it by its conjugate, 3 minus I. And so using our difference of two squares rule, our sum of two squares rule, we're going to have 3 minus I over 9 plus 1. So that's going to be 3 minus I over 10, which we can write as 3 over 10 minus 1 over 10I. Now that we have that information, let's pop that back into our equation. And now we can go ahead and solve. So 2 plus 3/10 is going to be 2 3/10. And then negative I minus 1/10 I is going to be negative 1 1/10 I. We can also use mixed numbers to represent this. So we could also do this as 23 over 10 minus 11 over 10I. So if I want to find the real component of z plus w, that's just going to be equal to 23 over 10, or we could write that as 2.3. Let's go ahead and solve this second part now. So we want to find the imaginary component of 3z plus 2w. We're going to need to find 3z plus 2w first. Now, again, I'm going to have to realize this denominator before I can actually multiply it by 2. I mean, you could do it beforehand, but since I already know that 1 over 3 plus I is equal to 3 over 10 minus 1 over 10I, I'm just going to substitute this straight into the equation. So we have 3 lots of z, which is going to be equal to 6 minus 3I, plus 2 lots of 3 over 10, which is going to be 6 over 10 minus 1 over 5I. So that's going to be equal to 6.6 minus 3.2I. And again, we could do this using an improper fraction, or we could do this using a mixed number. It doesn't really matter so much since the values that we get are going to work out the same. All right, so that is how we can use conjugates to realize the denominator. And then once we've realized the denominator, we can go ahead and we can perform a whole bunch of those simple operations. Oh, sorry, I've just forgotten. We need to do the imaginary component of 3z plus 2w. So that's going to be equal to negative 3.2i. All right, guys, I will see you in the next video.